Okay, in this podcast we're going to take a look at what effect complex ions have on the solubility of salts. Okay, so there's a number of things that affect how soluble something is. Sometimes we're trying to get more stuff to precipitate out, and sometimes we're trying to get more stuff to dissolve. So there's a number of tricks, chemist tricks, that can be used to try to get a shift in the equilibrium when something is dissolving. And some of those things that can be done are add other ions, common ions, change the pH. And the one we're going to talk about here is complex ions. So the formation of a complex ion always will increase the solubility of the salt. So if you want a salt to dissolve more, you can use a complex ion. And complex ions involve Lewis acids and bases. Alrighty. So if you remember from when we talked about this last unit, Lewis acids and bases are not defined as proton donors and acceptors like they were with Bronsted-Lowry or Arrhenius. In fact, they donate electron pairs or accept electron pairs. So if you remember, ammonia is a pretty typical Lewis base because it has this lone pair of electrons that's available to be donated. Okay, so it's not uncommon for ammonia to be the Lewis base involved in the problems that you'll see on the AP test. And the Lewis acid, therefore, will accept that pair of electrons. So, and those Lewis acids are often transition metal positive ions. Okay, so things like zinc plus 2, iron plus 3, copper plus 2. So this is a little diagram of what a complex ion would look like. Here we've got a complex of the copper plus 2 ions, and there are 4 hydrogen or ammonias attached to it. Okay, so that's what it would look like. So it's usually ammonia that's involved in the problems, but you could also have problems where you are using some other Lewis base, and that could include hydroxides or cyanide ions. Okay. So the whole idea is, let's say we have a beaker that has water in it, and we have put silver chloride in it. You know, we generally consider silver chloride to be non-soluble, right, according to the solubility rules. But in fact, even though we have mostly precipitate that falls out, there'll be some small concentration of positive and negative, positive silver ions and negative chloride ions. This looks like a kid's unhappy face, right? Okay. And so the KSP for that would be very low, very small amount of it will dissociate. So what you could do is, in order to shift the equilibrium to cause it to move to the right, to get more to dissolve, you could find ways to tie up the silver. And one way to do that is to add something that would act as a Lewis base, in this case ammonia. And what the ammonia does is it forms a complex with the silver, and you end up with Ag and NH3 And by pulling this silver out of this solution, it causes more of the silver to come off the silver chloride. More of it ionizes, right? So if you're pulling away this product, the Chatelier will say that you're going to shift the equilibrium to the right. And in fact, that's what happens. And as more and more of it complexes, more and more of the silver will dissolve. So that's the basic idea. So let's take a look at the problem that's in your assignments. Let me just turn to that page in my packet here. Okay, so it says, I'm going to get to the right page. All right, it talks about table 17.1. Let's take a look at... All right, I didn't include 17.1 here, but it's given to you on the sheet. It's behind one of the problems that you picked up on the paper. But this is what there's a list of a variety of complexes, and this is This is the one that I find. So what it told me in the problem from the table of KF listed, and these are equilibrium of formation. The F means equilibrium of formation. We want to calculate the concentration of Cu plus 2 in 1 liter of a solution that contains 0.001 molar of copper 2 ions in 0.1 molar ammonia. Okay, lots of information there. So if I look at that table on 17.1, what I'll see is I'm looking for something that has copper in it and ammonia. And I find this. This is the KF. The larger the KF, the more stable, larger KF, the more stable state complex. So this is a pretty high one, right? This is a positive number, 5 times 10 to the 12th. Okay. And it even gives me the equation for what's happening, and this is the complex that gets formed. It's 1 copper plus 2 ion with 4 ammonias, and the whole thing has a 2 plus charge. Okay. So there was some ionic compound that had copper in it that was in a solution. Copper 2 ions were floating around, ammonia was added, and we make this complex. Okay, so let's go see how we're going to solve this problem. So I can write the equilibrium expression for this equation right here, and it's going to be Kf, which is 5 times 10 to the 12th. Alright, why is that not working? Times 10 to the 12th is going to equal my product's concentration over my reactant concentration. And in all cases, these are aqueous, so they're all included, right? So the concentration of the complex over the concentration of the Cu plus 2 and the concentration of the ammonia. And because there's 4 of them, I need to raise that to a 4. Okay. And what I am trying to find is the concentration of Cu plus 2, right? That's what it's asking for here. Okay. So let's see what other information we have. We know that we are 0.1 molar NH3. Okay. And the other thing that we're told is that the concentration of Cu plus 2 in 1 liter of solution is 0.001. Now, when it forms a complex, this copper is still an ion. Okay, so it's saying a solution contains 0.001 moles of copper 2 ion. It's a little bit confusing because this is copper plus 2 and this is copper plus 2, but it says we're looking for copper plus 2 down here. So this must be from here, right? Must be from this. So as part of this, I have 0.001 moles in 1 liter, so that's 0.1 molar of this. So this is going to be 0.001 molar over the concentration of Cu plus 2 times the concentration of ammonia, which we know is 0.1 molar, but that is raised to the 4th. And all of that is equal to the Kf, which is 5 times 10 to the 12th. Okay. So Cu plus 2, 0.1 raised to the 4 power, so that's a caret 4, right, times 5 times 10 to the 12, is going to give me a copper concentration of, if I solve this for copper, it's going to be Cu plus 2 concentration is equal to 2 times 10 to the minus 12. Okay, so just a tiny little bit here. Okay, but I pull in a lot of this ion. Okay, let's take a look at another one. Alright, this is a little bit more complicated. It says, to what final concentration of ammonia must a solution be adjusted to dissolve 0.020 moles of nickel oxalate that has a KSP of 4 times 10 to the minus 10 in 1 liter of the solution. And it says, a hint, you can neglect the hydrolysis of oxalate because the solution is quite basic. Okay, so we've got 2 things going on. First, we are taking the nickel oxalate, which is a solid, and some of it ionizes, a small amount, right? It's got a tiny KSP, into Ni plus 2 aqueous, and the oxalate ion, plus the oxalate ion. Okay, that's also aqueous. And what we know is the KSP is 4 times 10 to the minus 10. And that's going to equal my equilibrium expression, which is going to be the concentration of Ni plus 2 times the concentration of C2O4 minus 2. Okay? And then I'm going to have that nickel is going to be pulled out because, whoops, there should be Ni plus 2 plus the ammonia. Whoops. Ammonia, not ammonia. Let me erase that because it looks messy. Erase the whole thing. Go back to my pen. Alright. So I have Ni plus 2. We add ammonia to that solution, and we are going to form. Now, if I go to table 17.1 again, I want to look for a complex that has nickel plus 2 and ammonia in it. And when I do, what I find is NiNH3, 6 ammonias on that, 2 plus charge, and it's, of course, aqueous. This is aqueous. This is aqueous. Right? And it gives me the Kf. Well, let's do it down here. Kf is equal to 1.2 times 10 to the 9th. And I need 6 ammonias here. It actually gives me this equation. And that's going to equal, let's write the equilibrium expression. So it's going to be this over this times this, right? So it's going to be nickel with ammonia. And that's a 2 plus charge over nickel plus 2. And over, oops, ammonia. And because there's 6 of them, I need to raise this to the 6th. Okay, and we want to find the concentration of ammonia, so we're trying to find this. Okay, so let's see what other information we have. Alright, so we are adjusting the solution to allow us to make this much of the nickel. So what that says is that whatever the complexing does to cause this reaction to shift is going to allow us to liberate 0.020 moles. Okay? So I'm going to end it with 0.020, okay? And that's going to be over NH3 to the 6th. But I need to find out how much nickel I have. Okay. So I need to do that by going back to this equation and using the KSP. Okay. So we know KSP is 4 times 10 to the 10th. I know that this is the equation. So let's see what we know. We know that we're going to result in 0.020 moles of this. So we're going to end up with that much of this ion. Things happen to the nickel, right? So what I can say is this is 0.020, and that I got to find out what my nickel plus 2 is because I just don't know. So if I solve for nickel plus 2, it's going to be 4 times 10 to the minus 10 over the concentration of the oxalate ion, and I'm going to get that nickel plus 2 concentration is equal to, let me see, it comes out to be 2 times 10 to the minus 8. Alright. Let's move this up a little bit. Alright, so I'm going to put that in here, 2 times 10 to the minus 8. Okay, and I'm trying to solve for ammonia this time. So I'm going to have, and this is all equal, of course, to 1.2 times 10 to the 9th. So I'm going to have 2.8 times 10 times 10 to the minus 8 times 1.2 times 10 to the 9th times ammonia's concentration to the 6th is equal to 0.020. I'm just cross multiplying this times this, right? So if I divide both sides by these, I'm going to end up with NH3 to the 6th is equal to whatever this comes out to be. So let's punch it. So it's going to be 2.8 second EE minus 8 times 1.2 second EE 9 gives me some number. I'm going to take 0.02 and divide by that number, and I get 5.95 times 10 to the minus 4. And then what I can do is take that number, and if I use my caret, I can raise it to the 1/6. That will give me the 6th root. Okay, I'm going to do caret 1 divided by 6, and that didn't work. Okay, so what did I do wrong? 2 times 10 to the minus 8th times 1.2 times 10 to the 9th times NH3. I think I punched it wrong. Let's just pause this baby for a second. Okay, I did that right. I just had written the answer wrong before. So if I do this, I end up with 0.307. And I really only want 1 sig fig, so that's all I'm given in my KSP, so it's 0.3 molar of Cu, or nickel in this case, nickel plus 2. Alright, that's going to do it.